Look around you. Plastics are everywhere. From the smartphone in your hand to the packaging of your food, plastics have become ubiquitous in our modern lives. These versatile materials are lightweight, durable, and relatively inexpensive to produce, making them indispensable in countless applications. From healthcare to transportation, construction to consumer goods, plastics have revolutionized the way we live, work, and interact with the world around us. However, this widespread use of plastics has come at a cost. The very properties that make plastics so desirable, their durability and resistance to degradation, also pose significant environmental challenges. Vast amounts of plastic waste end up in landfills, oceans, and ecosystems worldwide, taking hundreds of years to decompose and wreaking havoc on the environment. Understanding the journey of plastic, from its raw material origins to its final form, is crucial to addressing these challenges and developing sustainable solutions for the future. The story of plastic begins with small, simple molecules called monomers. These molecular building blocks are the foundation upon which the vast and diverse world of polymers is built. Polymers, as their name suggests, from the Greek poly meaning many and meros meaning part, are large molecules composed of repeating structural units, the monomers, linked together in long chains. Imagine a chain of paper clips, each clip representing a monomer. When many clips are linked together, they form a long, flexible chain, the polymer. This process of linking monomers to form polymers is called polymerization. It is a remarkable feat of molecular engineering that transforms simple, low molecular weight substances into materials with entirely new properties. The type of monomer used, the length of the polymer chain, and the arrangement of the chains themselves dictate the final properties of the plastic. This incredible versatility is what makes plastic so adaptable for a wide range of applications. One of the primary ways we create these remarkable materials is through a process known as addition polymerization. Picture a chain reaction, like a line of dominoes falling one after another. This is the essence of addition polymerization. It begins with an unsaturated monomer, a molecule containing a double or triple bond. This bond acts as a point of reactivity, a place where the molecule is eager to connect with others. The process is initiated by a catalyst, often a free radical, which acts like a spark, breaking the double bond in the first monomer and creating a highly reactive species. This activated monomer then attacks another monomer, breaking its double bond and forming a new bond between them. This process repeats itself, with each newly added monomer becoming activated and capable of adding another monomer to the growing chain. The result is a long chain-like molecule, the polymer. While addition polymerization resembles a chain reaction, condensation polymerization is more like a delicate dance, a series of carefully orchestrated steps that lead to the formation of a polymer. Unlike addition polymerization, which requires monomers with double or triple bonds, condensation polymerization can occur between monomers with two or more functional groups. These functional groups are specific arrangements of atoms that are capable of reacting with each other. During condensation polymerization, two monomers, each with at least two functional groups, react to form a covalent bond between them. This reaction also produces a small molecule as a byproduct, typically water or methanol, hence the name condensation polymerization. The newly formed dimer, now possessing at least two functional groups itself, can then react with other monomers or dimers, continuing the process and growing the polymer chain. This step-by-step process creates polymers with a slightly different structure and properties compared to addition polymers. The type of polymerization, the specific monomers used, and the conditions under which the reaction occurs all influence the final properties of the plastic produced. This incredible versatility is what allows us to create such a wide array of plastic materials, each tailored to specific applications. Some plastics, like polyethylene or PE, are very flexible and are used in plastic bags and packaging. Others, like polyvinyl chloride or PVC, are known for their durability and are used in pipes and flooring. Polystyrene, commonly used in disposable cups and containers, is lightweight and insulating, while polyethylene terephthalate, or PT, used in water bottles and clothing fibers, is strong and transparent. On the higher end of the performance spectrum are engineering plastics like polycarbonate, known for its impact resistance and used in safety glasses and electronics. and polytetrafluoroethylene, or PTFE, often known as Teflon, famous for its non-stick properties and heat resistance. From the mundane to the high-tech, the world of plastics offers a material for almost every need. The very properties that make plastics so versatile, their durability, resistance to degradation, and low cost, also contribute to their negative environmental impact. The sheer volume of plastic waste generated globally is staggering. Plastic bottles, bags, packaging materials, and discarded products accumulate in landfills, where they can persist for centuries, taking up valuable space and leaching harmful chemicals into the surrounding environment. The problem extends beyond landfills. Vast amounts of plastic waste end up in our oceans, forming massive garbage patches that threaten marine life and ecosystems. Seabirds, turtles, and marine mammals often mistake plastic debris for food, leading to starvation, entanglement, and ingestion of toxic chemicals. The breakdown of plastics into microplastics, tiny particles less than 5 millimeters in size, poses further risks, as these particles can be ingested by marine organisms, potentially entering the food chain and ultimately impacting human health. The environmental consequences of conventional plastics have spurred a search for more sustainable alternatives. One promising avenue is the development of bioplastics. Unlike traditional plastics derived from fossil fuels, bioplastics are made from renewable biomass sources, such as cornstarch, sugarcane, vegetable oils, or even algae. These materials offer a potential solution to the problem of plastic's persistence in the environment. Bioplastics can be designed to biodegrade, meaning they can be broken down by microorganisms into natural substances like water, carbon dioxide, and compost. This makes them a more environmentally friendly option, as they don't contribute to long-term pollution in landfills or oceans. However, it's important to note that not all bioplastics are created equal. Some bioplastics require specific conditions to biodegrade, such as industrial composting facilities, while others may only degrade partially, leaving behind microplastics. While bioplastics offer hope, improving recycling rates for conventional plastics is crucial for addressing the plastic waste crisis. Currently, only a small percentage of plastics are recycled globally. This is partly due to the complexity of plastic waste streams, which often contain a mix of different plastic types that are difficult to separate and recycle effectively. However, innovations in recycling technologies are emerging that could revolutionize how we manage plastic waste. Advanced sorting technologies such as optical sorters and artificial intelligence can more accurately identify and separate different types of plastics, improving the efficiency and effectiveness of recycling processes. Chemical recycling, another promising approach, uses chemical reactions to break down plastics into their constituent monomers or other valuable chemicals, which can then be used to create new plastics or other products. These innovations, along with increased consumer awareness and participation in recycling programs, are essential for closing the loop on plastic use and reducing its environmental impact. The story of plastic is a complex one, marked by both remarkable innovation and significant environmental challenges. While plastics have revolutionized our lives in countless ways, their indiscriminate use and disposal have created a global pollution crisis. Addressing this crisis requires a multifaceted approach that encompasses reducing plastic consumption, developing more sustainable materials like bioplastics, and revolutionizing recycling technologies to create a circular economy for plastics. Ultimately, shaping a sustainable future with plastics requires a shift in mindset, from a linear take-make-dispose model to a circular economy that prioritizes reducing, reusing, and recycling these versatile materials. By embracing innovation, promoting responsible consumption, and investing in sustainable waste management systems, we can harness the benefits of plastics while minimizing their environmental impact, ensuring that future generations inherit a cleaner, healthier planet.